The grating equation tells us which directions theta bright light will emerge from a ruled surface that has equally spaced lines separated by a distance d, the groove spacing. Imagine a row of equally spaced fence posts. If you shine a flashlight at the fence, bright spots appear at angles where the path difference between light reflecting off adjacent posts equals an integer multiple of the wavelength lambda. Mathematically, this condition is d sine theta equals m lambda, where m is an integer called the diffraction order. M equals 0, plus or minus 1, plus or minus 2, and so on. The zero order m equals 0 is simply the straight-through or specular beam. Higher orders are like echoes of the original color, each shifted further away from the center. The larger the wavelength, the larger the angle for a given order. The larger the groove spacing d, the smaller the angle. This simple linear relation is the foundation for all spectroscopic work with gratings. Diffraction gratings come in two broad families: transmission and reflection. In a transmission grating, the light passes through the slits or grooves. Think of a comb of tiny windows, and the diffracted beams emerge on the opposite side. In a reflection grating, the light bounces off the grooved surface, like a set of tiny mirrors. A second classification deals with the shape of the substrate. A plane grating is flat. It is the most common type and works like a flat ruler with many teeth. A concave grating is curved like the inside of a dish. The curvature gives the grating both dispersive power and focusing ability, so it can act as a combined grating plus lens, sending each wavelength to a different point on a focal plane without extra optics. In practice, transmission gratings are often used in compact, low-power spectrometers, while reflection gratings dominate high-resolution laboratory and astronomical instruments because they can handle higher power and offer better blaze control. Dispersion describes how fast the diffraction angle changes with wavelength. Angular dispersion is defined as d theta over d lambda equals m over d cos theta, obtained by differentiating the grating equation with respect to lambda. It tells you how many degrees or radians you move on the sky when the wavelength changes by a small amount. Linear dispersion translates this angular spread into a physical distance on a detector placed at a distance f, the focal length of a camera lens, or the radius of curvature of a concave grating. The linear dispersion is dl over d lambda equals f times d theta over d lambda equals fm over d cos theta, where L is the position on the detector. An easy analogy is a prism that spreads white light into a rainbow. The steeper the rainbow, the higher the dispersion. In a grating, higher order larger m or finer grooves small d increase both angular and linear dispersion, making spectral lines farther apart and easier to read. Resolving power, R, measures how well a grating can separate two close wavelengths lambda and lambda plus delta lambda. It is defined as R equals lambda divided by delta lambda. The classic derivation starts from the condition that two wavelengths are just resolved when the maximum of one diffraction order coincides with the first minimum of the other, Rayleigh criterion. Using the grating equation for order m and counting the total number of illuminated grooves n, the angular separation between the two wavelengths is delta theta equals m times delta lambda divided by d cos theta. The width of a diffraction peak, its angular half-width, is approximately delta theta equals lambda divided by n d cos theta. Setting delta theta equals delta theta gives m times delta lambda divided by d cos theta equals lambda divided by n d cos theta, and hence r equals lambda over delta lambda equals mn. This remarkable result shows that resolution improves linearly with both the diffraction order and the total number of grooves that are illuminated. In real devices, n is the product of the groove density, grooves per millimeter, and the illuminated width of the grating. The grating can only produce orders where the path difference condition does not exceed the groove spacing. From the grating equation, the sine function is bounded by 1. So the largest order that can physically appear satisfies absolute value of sine theta less than or equal to 1 implies absolute value of m times lambda less than or equal to d. This is called the order overlap condition. If you try to observe a wavelength that would require absolute value of m times lambda greater than d, no real angle exists, and the light is not diffracted into that order. When several wavelengths are present, higher orders of shorter wavelengths can overlap with lower orders of longer wavelengths. For example, the second order of 400 nanometers overlaps the first order of 800 nanometers if D equals 1 micrometer. Designers avoid this by using order sorting filters, or by choosing D so that the desired spectral range stays within a single non-overlapping order. Free spectral range, FSR, is the wavelength interval between two successive orders of the same diffraction angle. It tells you how wide a wavelength band you can record before the next order starts to repeat the pattern. For a given order M, the free spectral range is delta lambda sub FSR equals lambda divided by M, derived from setting M lambda equals M plus 1 times lambda plus delta lambda and solving for delta lambda. The spectral bandwidth that a detector can actually capture is the smaller of the free spectral range and the instrument's own wavelength coverage. In a high-order spectrometer, the free spectral range becomes small, meaning the instrument can only view a narrow slice of the spectrum at a time, but the resolution within that slice can be very high because R equals Mn is large. A blazed grating is engineered so that most of the incident energy is sent into a chosen diffraction order, much like how a tilted mirror reflects light preferentially in one direction. The blaze angle beta is the tilt of each groove facet relative to the grating surface. When the incident angle, alpha, and the diffraction angle, theta, satisfy the Littrow condition, alpha equals theta equals beta, the groove facet acts like a tiny mirror and the efficiency in that order can exceed 70 to 90%. The groove profile, triangular, rectangular, sinusoidal, determines how the blaze behaves. A triangular shape gives a well-defined blaze, whereas a sinusoidal groove spreads light over many orders. Diffraction efficiency is the fraction of incident power that ends up in the desired order. It depends on wavelength, blaze angle, polarization, and groove depth. In practical spectrometers, selecting the proper blaze angle ensures that the wavelength region of interest is captured with maximal brightness, reducing exposure time and detector noise. A transmission grating has 1,200 grooves per millimeter. D equals 833 nanometers. Find the first order diffraction angle for lambda equals 500 nanometers. D sine theta equals M lambda. Therefore, sine theta equals 1 times 500 nanometers divided by 833 nanometers equals 0.60. Theta is approximately 36.9 degrees. Example 2. For the same grating, calculate the resolving power needed to separate lambda equals 600 nanometers from lambda plus delta lambda equals 600.1 nanometers in second order. M equals 2. Required R equals lambda divided by delta lambda. That is 600 divided by 0.1 equals 6,000. Since R equals Mn, N equals R divided by M, which is 6,000 divided by 2 equals 3,000 grooves. If the illuminated width is 25 millimeters, the needed groove density is 3,000 divided by 25 millimeters equals 120 grooves per millimeter, which is satisfied because the grating has 1,200 grooves per millimeter, so the instrument easily meets the requirement. Example 3. Determine the free spectral range for the first order at lambda equals 800 nanometers. FSR equals lambda divided by M, which is 800 nanometers divided by 1 equals 800 nanometers. Thus, the instrument can record up to an 800 nanometer bandwidth before the second order starts overlapping. Example 4. A reflective blazed grating has a blaze angle of 15 degrees. Using the Littrow condition, alpha equals theta equals beta, find the wavelength that is maximally diffracted in the first order. From the grating equation with alpha equals theta equals beta, 2d sine beta equals m lambda, therefore lambda equals 2d sine beta. If d equals 1 micrometer, lambda equals 2 times 1 micrometer times sine 15 degrees, which is approximately 0.52 micrometers, 520 nanometers. Therefore, the grating is most efficient around green light. These problems illustrate how the formulas are applied to obtain diffraction angles, assess resolution, compute required groove counts, and understand the bandwidth limits of a grating.